In this video, I am going to define definite integral. So let's say we have a function f that's well defined on some interval a comma b. Well defined in this interval, closed interval a comma b. Now what we are going to do, we are going to take this interval and subdivide it into smaller subintervals, each of them being equal length, and let's call that length to be delta x. And depending on how many subintervals I want, okay, I'm going to represent it by an n. So how am I going to find it? B minus a divided by n. N is the number of subintervals that I want. So that's my delta x. And then I kind of label the boundaries of each of these delta x's as follows. So x0 is the starting point A, then x1, x2, x3, dot, dot, dot. And the last one, x sub n, which is going to be my B. Okay. Now let's assume that x sub I star is a point in the ith delta x. So that means in this interval, x sub I minus 1 comma x sub I. So x sub I star is a point in that interval. Given these conditions, we define the following. We define, so this is a definition, remember, we define definite integral from point A to B. From point A to B as the following. Integral A to B f of x dx, which is, by the way, defined as limit n approaches infinity summation I is equal to 1 to n f of x sub I star multiplied by delta x. So this is the official definition of definite integral. Now let me kind of elaborate on the left side here. So this is actually, for now, think of it as a symbol, okay? That represents the definite integral, and I'm gonna break it down further shortly what these things mean. So if you have a function that's well defined on some interval, closed interval AB, and you subdivide this interval into smaller intervals or smaller subintervals, each being delta x, by following this formula b minus a over n, and label the points, boundary points of each of these intervals starting from x0 and ending at xn, representing b, and x0 star x sub 0 representing a. So, and let x sub I star be any point in that interval. Okay, you probably have seen left point, right point, or midpoint, but here we have no restrictions. X sub I star is any point. Then we define definite integral from point A to point B as follows. Okay, A to B integral. So this is how we read integral A to B f of x dx, which is going to be equal to limit n approaches infinity summation I is equal to 1 to n f of x sub I star times delta x. So in essence, you're finding the limit as n approaches to infinity of this summation. If this limit exists, so if the limit exists, then we say f is integrable in a comma b. Okay, so if the limit doesn't exist, of course it's not integrable. So now let me go ahead and label some of the things. So f of x, this here is called integrand. Integrand. Okay. A is lower limit of integral. Okay, so lower limit. And B is the upper limit. Upper limit. And together A and B are called limits of integration. And this little dx sitting down there, it just indicates that it's a small change. It will become clearer down the road. This is just a small change in x. However, for now you can just bundle it together with f of x. Is just one thing. But later on we will find out that this is called small change. We call it differential or differential change. And this thing is nothing but elongated s. So this is elongated, the letter s. So it was invented by Leibniz. Leibniz. Leibniz invented it. Actually, I shouldn't say invented it. It's not an invention, just using a symbol, but rather he used it, and we happen to use it even to this date. So that's just elongated s that denotes integral, okay, or integration. Now the summation, this summation, which is summation I is equal to 1 to n f of x sub I star delta x. This is called Riemann sum, named after German mathematician Riemann. So this is called Riemann sum, and this is just a sum for finding rectangles, nothing special. You have seen it when we are doing the integral by approximating, or finding the area rather by approximating. So this is how we define definite integrals. Okay, so we have a well-defined function. Just to summarize, well-defined function on closed interval AB, and define delta x to be b minus a over n, and take a random point in any interval, okay, in a particular interval. So x sub I x sub I star is a random point in this closed interval, and we define integral of the function f from a to b as a limit n approaches infinity, limit of this summation. That's how we define it. So look, if you look at it, this is kind of like the height, and this is the width of the rectangle. And as n goes towards infinity, this delta x becomes smaller and smaller, and in the limiting case, the value we get is actually defined as integral, and that is, by the way, you will see area under the function, between the area between the function and the x-axis. So if you have a function like this, integral from a to b is gonna give you this area. I hope that this discussion was helpful. Thank you very much.